Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 410, Split Array Largest Sum. Before we get into this problem, I just want to say that this question is very similar to three that I've already solved on my channel. Those being cutting ribbons, capacity to ship packages within D days, and Coco eating bananas. Those questions are all mediums on Leetcode. This question, however, is a hard. If you're having trouble understanding the algorithm, go and watch one of those three videos, come back to this one, and hopefully it should make a lot more sense because the way that we solve it is very similar, although this question is a little bit trickier, and that's why it's rated a hard on Leetcode. But the approach we're going to take is basically the same. Anyway, let's read the question prompt. Given an array nums, which consists of non-negative integers and an integer m, you can split the array into m non-empty continuous subarrays. Write an algorithm to minimize the largest sum among these m subarrays. So let's look at an example. If we're given nums equals 7, 2, 5, 10, and 8, and we're told that we have to split it into two subarrays, what would be our answer here? Well, let's figure out all the subarrays we can make and what their sums are going to be. So we know that it has to be non-empty and it has to be continuous. So since this is length 5, we could either have a subarray of 1 and 4, we could have 3, 2, we could have 2, 3, or 4 and 1. So let's build those and check what the sums would be. Excuse me. So let's do 1, 4. So we could split it. So one subarray has 7. The other one would have 2, 5, 10, and 8. So 2, 5, 10, and 8. And the sum here, the sum here is 7. This is 7 plus 10, 17 plus 8. So remember, we're looking to minimize the largest sum among these subarrays. So the largest sum among these two subarrays would be 25. What about, okay, we're going to go 2 and 3 now. So we're going to go 7, 2, and the rest would be 5, 10, 8. So obviously this side is bigger because this is 18 plus 5. So this is 23 is the largest sum among the two subarrays. And now let's go 3 and 2. So we go 7, 2, 5. And the other side would be 10 and 8. So this side is equal to, what is it? 14. This side is 18. So this is the larger side. So this is 18. And then we have 4 and 1. So we would go 7, 2, 5, 10, and 8. So this side, this is 7 plus 2, 9, plus 5, 14, plus 10, 24. So we can see that the way to split it, which minimizes the largest sum among the m subarrays, is going to be this one, because the largest sum among the two subarrays is 18. So this is our answer here. But how in the world do we derive this in an efficient manner? Because we can't just try every single possible combination. If m is really big, this is going to be super computationally expensive, right? This is going to be a factorial level time complexity, and that's not really the best solution. So let's think about if we can do better than that and how we might derive this in an intuitive manner. Okay. We read the question prompt and we looked at an example, but it's not exactly intuitive how we might find an optimal solution, because trying to go through all possible combinations is going to be a ridiculously expensive procedure, and we can't afford to do that if we want to find some sort of optimized solution. So let's think about how we might do this, and let's break it down in an intuitive manner. What are we trying to solve here? We're trying to minimize the largest sum among these subarrays. So some way we need to do something such that we find this largest sum. So let's set up our search space for the actual sum. What is the smallest possible sum that we'd want to work with? Well, in the worst case, our largest sum could just be one number. If the entirety of the rest of the array is negative numbers, so some negative number, and this is positive, then this will always be the largest sum that we have in an array, right? So it shows that our left boundary here should be whatever the maximum of our nums is, right? And the reason that we have that is because that we would just split it into a subarray of length 1, and then we could split the other ones however many times we need to make m equals 2. So this is the case where the rest of it is negative and we just have positives on one side. So that's going to be our left boundary. Whoops, let me select my pen here again. So the left boundary we're going to say is the max of whatever nums is. And what is our right boundary going to be for the search? Well, the largest thing we could make is going to be the sum of the entire array, right? So this is the case where, that's our right boundary, but we couldn't really use that unless m equals 1. So, I mean, this is the maximum we could possibly have, right? This is the largest possible sum we could get with this entire array. We can't go over the sum of nums. So that, is pretty intuitive why the right boundary is the sum of nums. That's the largest possible sum you can get. And this is going to happen in the case that m equals 1. So we have this, search space. So what is it for our problem here? So it's basically, so what's the maximum of nums? It's going to be 10. And what's the maximum sum we have here? So 7 plus 2, this is 9, plus 5, 14, plus 10, 24, plus 8, 32. So that means that we have the numbers between 10 and 32 to work with, right? This is our search space. And essentially what we want to do here is, because m is fixed, we're going to pick a sum. And we're going to pretend like this is actually the largest sum that we can work with. And what we're going to do is we want to check whether or not we can actually get m subarrays if we split using that sum. So what we're going to do is, let's say we pick 10 as our sum here, right? What we're going to do is we're going to go into some function which is going to check whether or not the sum works for us. So we're going to go, okay, how many continuous subarrays can we make such that the maximum sum of one of those subarrays doesn't exceed 10? So let's go to our numbers here, and we need at least one subarray, right? We're never going to be given m that equals to 0. It's in the problem description that actually m is going to be at least 1. So we know that we're going to have at least one subarray here that we can build. So we know that the maximum we can have is 10 for a subarray. So let's start making a continuous subarray. And remember, it has to be continuous and non-empty. So we can have 7 and 2. So that's going to give us a subarray of basically 9. And if we try to add 5 to it, it's going to become a sum of 14, which we can't have because the maximum is 10. So that means that one subarray has to be 7 and 2. So that means that we have one subarray built. Now we can continue. So we go 5, and that's another subarray. But if we try to add 10 to it, we'll have 15. And obviously our maximum sum is 10, so we can't have that. So 5 has to be on its own. So 5 is another subarray. And then we try 10, and 10 is fine because it's less than or equal to this, which is allowed. So we now have a third subarray, and then we have the 8, which is the last element, so it has to be on its own. So we have 4 subarrays. So we could split, if we were using a sum of 10, this array into 4 continuous subarrays. And remember, it has to be continuous and non-empty. This is why we're going from left to right. We can't just cherry pick elements as we please. So we have to be basically continuous, right? So since we made 4 subarrays, that exceeds our budget of m subarrays, which in this case is 2. So this solution would not work. So 10 would not work. So that means that we could go to 11 and try that, do the same thing, and keep going up until the first point where we actually find a solution, which we saw from earlier was going to be at 18. Now, if you've seen my other videos, cutting ribbons, capacity to ship packages within D days, or Coco eating bananas, you'll remember that each one of those problems had a setup similar to this, where we were searching some space from left to right. And what you'll notice is that these numbers are sorted in an increasing order, right? 10, 11, 12, 13, 14, all the way up to 32. So since this range is sorted, there's actually no reason for us to do these hops by 1, increasing each time. Because it's sorted, we can actually do a binary search here, right? Binary search over this search space, with this being our initial left point, this being our initial right point, and remember, we find a midpoint, try that. If it's too big, then we either move to the left or to the right based on the problem, and that way we can cut our search down to log n time, where n is the length of this search space, and then we have to multiply that by this function, which is going to check whether or not we exceed our budget. And since this is going over, you know, the nums from left to right, this is going to, this is going to be a big O of n. And then we should actually just call this S, where S is the actual search space, because it's not exactly going to be n, so search space. So that way, we can set up our solution to have n log s runtime. Whereas if we were just scanning linearly through this, this would cost, you know, big O of s, where s is the amount of elements in this range, so times big O of n, which could potentially be, you know, some sort of like n squared solution if s is equal to the length of this array here, which actually s should most of the times be bigger than n. So this solution is probably going to be quadratic. So we can bring it down to n log s, which is actually going to be our optimal solution. So let's go to the code editor and actually set this up. Like I said, this problem is going to be really similar to how we solved those other 3 questions in that we have the binary search. The only tricky part is really just setting up this function to check the condition here, but I think it's basically the same code as capacity to ship packages within D days. It's going to be the same idea. So if you remember how to solve this one's going to be a piece of cake. So let's go to the code editor. We'll write the code. We'll talk about the time and space complexity, which I guess we already did here. I guess I told you that it's going to be n log s. And then what we're going to do is, like those other 3 problems, we're going to go back into this diagram, and I'm going to walk you through the binary search step by step so you can see why we set the bounds like we do, how it works, and then how we're actually going to be sliding our left and right pointers up or down based on the condition of, you know, our current state of the binary search. And then we'll see how we're going to converge to our answer in case it doesn't really make sense from the code. Sometimes it helps to see it visually, and that's what we're going to do. So I'll see you in the code editor where we're going to write the code. Okay, we're back in the editor, and now let's write the code. So remember that we're doing a binary search here, so we need left and right endpoints. So remember that the left is going to be the maximum of our numbers here, and this is going to be the case where m equals 1, where basically we just want to find the maximum of whatever the numbers is. So we're going to say left equals max of nums, and remember that the right is going to be the largest possible sum we could get is just the sum of all the numbers. So sum of nums. Now we need to actually set up the binary search. So we're going to say while left less than or equal to right, and we'll go over why it's less than or equal to right when we go to the diagram. And remember that in a binary search, you need to find the midpoint. So we're going to say, what are we looking for? We're looking for the largest sum. So that's, you know, we were trying all possible large sums between, you know, max sums and the sum of nums. So we're going to say candidate sum is going to equal to left plus right divided by 2. And now what we're going to do is, remember, we need a function to check if we use this candidate sum, can we get m subarrays? So we're going to say, or sorry, at least m subarrays, right? We're going to say if self dot, you know, min subarrays required. We're going to say, we're going to pass in the numbers, and we're going to pass in the candidate sum, and we're going to check whether or not this is less than or equal to m. If it is, that means that our sum here is actually too small because we need exactly m subarrays. So if it's less than or equal to, well, if it's less than, then it's too small. If it's equal to, then it's a candidate solution, and that could be our answer, but we still need to move to the left because we don't know whether or not there's a better solution. Even though it equals to m, there could be another solution to the left of it, which also equals to m and has a smaller sum. So that's why we need to move our right down in this case if it's less than or equal to m. So we're going to say right is going to equal to, basically, we want to move it from our candidate sum minus 1. So we want to say candidate sum minus 1 because we don't want to go, we only want to move it down 1 in the case that that was a potential solution there. So because this can be a potential solution, we also need to set this equal to our answer. So anytime we find this case, it could be a potential solution. So we want to say ands equals to max, so we'll say candidate sum. And we will then keep going with the binary search. Otherwise, if the candidate, if we got too many subarrays, then that means that basically we need to increase the sum and try to bring the number of subarrays down. So we're going to say left is going to be equal to max, oops, not max, so candidate sum plus 1. So we're going to move that up by 1 and then redo the binary search. So what we're going to do at the end, once this while loop breaks, we'll have found our answer. And remember that answer is being stored in our ands variable. So that's all we have to do, is simply return our answer. Now what we need to do is actually define this function min subarrays required, which is going to take a candidate sum and tell us how many subarrays we could form if we use that sum as our kind of largest sum among the two subarrays that gets built. So let's define that. So we'll say def min subarrays required and self nums and then candidate sum. So we're going to have our current sum equal to 0. And remember, what we need to do is we need to go from left to right and try to build our subarray as big as possible until we get to a point where the sum of our subarrays so far exceeds candidate sum, in which case we can't take that last element that we just took that pushed us over the candidate sum. We have to make a subarray of everything before that. And then we're going to keep doing that and basically see how many subarrays we make. So we're going to do it in a greedy manner. And if you remember, this is basically the same way we solved capacity to ship packages within D days. It's the same idea. So if you don't quite get this one, go back to that problem and look at it, because I think I explained it a little bit better there. So remember that we are going to have, based on the problem description, at least one M here. So that means that our splits, the amount of splits we can get, or the amount of subarrays, maybe we'll just call it subarrays, subarrays is going to be at least 1, because we know that M has to be at least 1, so we need to at least have 1 subarray. We can't have 0, right? They have to be non-empty continuous subarrays, so we know that we'll at least have 1 subarray here. Now what we need to do is we need to say for num in nums, we're going to say if the current sum plus whatever number is actually less than or equal to the candidate sum, then we're allowed to take this number, because remember, we are allowed to go up to candidate sum where we're allowed to have it equal to, and that's fine for a subarray. But if it exceeds that sum, then we know that it's too big and we can't take the number that we just took. So if taking the current number would still have us possessing a valid sum, then all we need to do is actually just increment our current sum by the number and continue on through the array. If we have the case that adding the current number would actually push us over the candidate sum, then we know that we can't take this number, and then this number will be part of our next continuous subarray, and we need to increment our subarrays by 1, because we clamp the previous subarray up until this number, and then we continue on with the next one, and we have to reset our current sum to whatever num is, because that would be the start of our new subarray, and that's the current sum of the next subarray. So we're going to say cur sum is going to equal to num, and we need to increment our subarrays by 1 because we've just formed a new one. And at the end, all we want to do is return our subarrays, and this is what's going to get used here to check whether or not our current candidate sum is actually valid. So let's just kind of run this, make sure we haven't made any but subarrays. 3 R's here. Okay. Double check we still haven't made any spelling bugs. Okay, cool. So we should be ready to submit this, make sure it works, and it does. Cool. So before we go back to the diagram to kind of draw this out step by step, let us actually talk about the time and space complexity here. So the time complexity of this algorithm to calculate the subarrays required is going to be big O of n, right? It's going to be big O of n because we have to go through this list from left to right each time and do some computations. So it's going to take us big O of n time to do this. And remember that we have a binary search here, and inside of this binary search, we're calling this min subarrays function. So we know that this part is big O of n here, but the binary search we know is going to be log of something. And what is that something? Well, we have a search space from our left here, which is the max numbers, and right, which is going to be the sum of our numbers. So we can consider that span, the length of this array, we'll call it S, where S is the search space. So that means that our time complexity here is going to be n log S for the entire algorithm. What is the space complexity? Well, we don't actually create any extra data structures. The only variables we create are really just pointers to, I guess, the left, the right, and then we have this cur sum and subarrays, and these are all just constant space allocations. So our space complexity is actually going to be big O of 1. And that's going to be your time and space complexity for this algorithm. Now, like I promised you, we're going to go back into the drawing board and we're going to go through the algorithm step by step so you can see why we set the conditions, less than or equal to right, and you can see why we're moving down the right and the left the way that we do based on the current conditions. And we'll walk through it step by step and basically go through the algorithm, and you can see visually why it works, because sometimes I find it's a lot easier to visualize it. If you've never seen this type of problem before, it can be a little bit confusing, but once you see the diagram, it should make sense. So I will see you back at the drawing board, and we're going to go over this step by step. Okay, we're back in the drawing board, and I have the code here for the problem on the left, and we have our kind of example that we went through earlier on the right here, and we're going to walk through this and basically walk through our solution. So the first thing that we do is we set our left, which is going to be, let's just split this out here. We're going to say that the left, remember, is going to be the maximum of our array here. So what's the maximum? It's going to be 10. And remember, our right is going to be equal to the sum of this array. So 7 plus 2, 9, plus 5, 14, plus 10, 24, plus 8, 32. So we have our right is 32. And now we're going to set, while left is less than or equal to right, which it is because 10 is less than or equal to 32. So we basically have, we now need to find our midpoint. So 10 plus 32, what is that going to be? So let's say 10 plus 32, so that's 42. 42, and then we divide by 2, so this is going to equal to 21. So the candidate sum is going to be 21, and now we need to go into our function here and basically figure out whether or not we can use 21 and whether or not we can get 2 subarrays here. So our current sum is going to be 0, so cur sum is 0 because we actually haven't started, and we have, we'll say SAs for subarrays 1, right? So now let's start building. So the first number is 7, so our current sum now becomes 7, and we're still not over our threshold of 21, so we keep going. Now we get 2, so our current sum is 9, and then we get 5, so next it's 14. Then we get to the 10, and we see that if we added 10, we would get 24, so that's not a valid solution. So we need to clamp our subarray. So the first one becomes 7, 2, and 5. And, we have our 1 subarray here. So we would basically get 2 subarrays. So we increment our count to basically 1. We increment it by 1 and we get 2. So this is our first subarray, which means that we can now we can keep going. So we reset our sum to 10, and then that's fine. And then we add 8 to it, and we get 18. And actually our function ends here. So that means that we keep going. So we've made 2 subarrays in total. And you do have the option of either starting subarrays at 0 and then returning subarrays plus 1 to account for it. I guess it's a little bit more intuitive because in the beginning we had no subarrays formed, but technically it was 1, and then we formed that first one, we have 2, but we've only formed 1. It's really up to you, but you can see that on the last one, if you don't actually form a subarray because the list ends, you won't increment that count. So you will already have taken into account that case when you do it. It's more of personal preference. It doesn't really matter how you do it. Either way, you're going to get the same solution, whether or not you started off at 0 and then just return subarrays plus 1 at the end, or you just do 1 and return subarrays. It's up to you. Anyway, we see that we got 2 here from our subarrays, and we return this, and we see that, okay, is 2 less than or equal to m? It is. So this could be a potential solution, but we want to go to the left and now see if there's anything smaller. Because we're trying to minimize the largest sum, there's no point of us trying a larger sum. If we know that 21 works, because it's a binary search, we know that anything above 21 is pointless to try because we're trying to minimize this sum. So why would we try 23, 30, all that stuff? Because we know it's already bigger and it could work, but we're looking to minimize it, right? So there's no point of us going to the right. So that's why we move our candidate sum down by 1. So we're going to say that the candidate sum, so we're going to set our right now equal to the candidate sum minus 1. So we're going to say that 21 minus 1 is 20. And then we're going to say our potential answer is going to be the candidate sum. So we have this ands variable, and it's going to be 21, because this could be a potential answer. Now we go through the binary search again. So we go through the binary search again, and this time we have, okay, 10 plus 20 as our right endpoint, and 10 is still less than or equal to 20. So we can continue here. So we have 30 divided by 2, and we get 15 here, right? So we're going to try with 15, and we're going to go through the same process here. So the current sum is going to start with 7, and we have one subarray here. And then 7, we add 2 to it, we get 9. Then we add another 5 to it, we get 14. And then we try to add the 10. Obviously that will take us to 24. We can't do that. So then we have one subarray here. We increment our count. So this is now 2. And then the next subarray starts at 10. We try to add the 8 to it, but that would give us 18. That's not allowed. So that means that we have to make another subarray with this 10. Our count is now 3. And then we have 8. So 8 will be the last subarray. So we have the 3 here, right? So we have the subarray with 7, 2, 5, then 10 on its own, and then 8 on its own. So those are the subarrays we could form. So from this one, we would return 3. But obviously 3 is greater than our m here, so this is not a valid split. So in this case, what we want to do is, because this is not a valid split, there's no point of checking any smaller sums because they would also not be valid. So that means that we want to increase our left pointer. So our left becomes candidate sum plus 1, so it becomes 16. And then we go through the loop again. So 16 and is still less than or equal to 20. So we go through again, and then we find the midpoint. So oops, you can't see that actually. So we'll say 16 plus 20 equals to 32, divide by 2 to find the midpoint, and we get 16. So now we're going to try with 16. So again, we have, we do 7 plus 2, 9, plus 5. That's going to give us 14 for the sum here. We try to add the 10. We can't do that, so we increment our subarray count. So it was originally 1, now it's 2. Then we add the 10 on its own. We try to add the 8 to it, but that would give us 18. So this has to be its own subarray. So we go to 3, and then the 8 stays on its own. So we would again return 3 from this function. And 3 is still greater than m, so that means that 16 is not a valid one. So that means that we move our left up 1. So left is 17, and we're going to go through the process again. So 17 plus 20 is going to equal, oops, this should actually, oh fuck, did I mess this up? 36. This should actually be 18. Oops. Okay, let's go back through that again. My bad. Apparently can't do math today. So this is actually still 16 because we messed up. Okay, so this is, let me just erase everything and we can go back and pretend like that didn't happen. Apparently I can't do math today. Okay, so 16. So this actually should be 36. So this is 18. My bad. So our midpoint is now 18. So we try with 18. And okay, so we have 7. Then we add the 2, so now it becomes 9. We add the 5, it becomes 14. Our subarray count is actually equal to 1. And then, right, we try to add the 10. Obviously, that would take us 24, which is greater than 18. So we increment our subarray count 2, and then we get the 10. And then we add the 8, because we can actually have 18 now. So we have 2 subarrays here, right? The 7, 2, and 5, and then 10 and 8. So we have our 2 subarrays. We return that. So 2 is actually less than or equal to 2. So that's good. So we're in this condition up here. So now we set our right equal to whatever the candidate sum was, minus 1. So this becomes 17. And then we say that our new answer is now this candidate sum. So we found a better answer than the 21 we had before, which is the 18. Now we're going to do 16 plus 17 equals to, what is that? That's going to be, I think, 33. Divide by 2, and this is integer division. So when we do this, this is going to be what? 16.2. This is going to be 16, and we're going to try 16. And okay, let's try with 16. So we have 7, 2, 5, so that's 14. We try to add the 10. That doesn't work, so that means that we increment our subarray count. So now we have 2. Then we try with the 10. That's fine. Actually, we did that before. We try to add the 8 to it. We can't because it would be too big. So then we increment our count by 3, and the 8 is on its own. So we can see that we return 3 subarrays here. and that's greater than RM. So that means that we have to increase our left by 1, so 17. So we're going to try one last time with 17 because remember it's less than or equal to. So 17, oops, you can't see that either. Let's see. So 17 plus 17, that's going to be equal to 34. Divide by 2, that's going to be 17. So let's try with 17 as our potential one, and I'll make some extra space here. Sorry, it's getting a little messy. So 7, we can have that. We can add the 2 to it, so we get 9. We can add the 5, we get 14. When we try to add the 10, obviously that doesn't work because we'll get 24. So we need to increment our subarray count. So we have 2 now, and we have the 10 on its own. We try to add the 8 to it. That'll be too big. So we have 3 subarrays, the 7, 2, 5, the 10, and the 8. So we return 3 from this function. And remember that this is too big. So we're in this case, we'll remove the left equals candidate sum plus 1. So now left equals to 18 because our candidate sum was 17. And now left is no longer less than or equal to right, which is 17. So now we break and we can simply return our answer, which is 18. And remember that that was what we expected earlier when we did the problem. So, hopefully it hasn't gotten too messy here with all these diagrams, but you get the idea. This is basically how we're going to do it. We've walked through the solution. Hopefully it makes sense how it works, how you set up the binary search, and why it works in the way that it does. And we've written the code, we've gone over the diagram, so you should have a pretty good idea of how to solve this problem. If not, remember, you always have those 3 other questions where we did the exact same thing. We wrote the code and we went over the actual drawing out the solution line by line to how to derive it and showing that the binary search works. So go watch those other videos if this one was a little bit unclear. Otherwise, I just want to thank you for watching. If you enjoyed this video, please leave a like and comment. It really helps with the YouTube algorithm. If there's any videos you want to see, just leave them in the comment section below. If they're not too ridiculously hard, I will probably get to them. There's some questions on Leetcode where even if I look at the solution, I have absolutely no idea how to solve them. So if you ask for one of those questions, I'll do my best, but may not be able to do it. Otherwise, please subscribe to the channel so you don't miss future videos. And thanks for watching. Have a nice day. Bye.